Hello everyone, I am Pradnya and in this video we are going to study chapter 2, that is data representation. In this chapter we are going to get the knowledge of different types of number system and the conversion of number from one number system to another number system. So let's get started. What is number system? Nowadays, technology, all types of businesses and other areas also dealing with the huge quantities, and we need computer to handle the quantity, and computer represent these quantities in the form of digits. So to represent digits, we have different types of number systems. So what is number system? It is a method of expressing numeric values. So there are 4 types of number systems we have to study in this chapter. The first one is decimal, the second one is binary, and there are other 2 number systems also, that is octal and hexadecimal. So let's study these number systems in detail. The first one is the decimal number system. This is the most commonly used number system we used in day-to-day life to count the money, to measure height, width, and even to note down the time. It has total 10 numbers, that is 0 to 9, and other higher number we can design with the combination of these digits. As it has total 10 numbers, the base of this decimal number system is 10. What is the base? The total number of symbols in a number system. It is a positional number system, means the value of the digits depends on its position. So let's take one simple example to understand the concept of position. I am taking one example. Consider a number that is 123, and you have studied in maths in the lower grade how to calculate the place value of the numbers. So you know 3 at the unit place, 2 is at the tens place, and the 1 is at the hundred place. We can express this position in the form of power of 10. So this is 10 raised to power 0, this is 10 raised to power 1, and this is 10 raised to power 2. Any number has power 0 is equals to 1. Now to calculate number, we have to just multiply these positions with the respective digits and then add it up. So we have to multiply 10 raised to power 1 to 2 and 10 raised to power 2 to 1 and then add it up. So it will be 1 into 10 raised to power 2 plus 2 into 10 raised to power 1 plus 3 into 10 raised to power 0. So 10 raised to power 2 will be 100, 2 into 10 will be 20, and 3 into 1 will be 3. So we got 123 answer. So you can see here we got the same number. In this number, among all the digits, 1 has the highest weight, that's why it is known as MSB, that is most significant bit, and 3 has the lowest weight, that's why it is known as LSB, that is least significant bit. Now let's try to understand how we can solve it for the fractional part. I am going to take the same number with some fractional part. So 123, let's take 0.45. You know 4 is at the 10th place and the 5 is at the 100th place. So we can write in the form of 10 as 1 by 10 and this will be 1 by 100. So there is another way to write it. This is 10 raised to power minus 1 and this is 10 raised to power minus 2. Now let's multiply these positions with the respective digits. So we will get 4 into 10 raised to power minus 1 plus 5 into 10 raised to power minus 2. So we can write it as 4 divided by 10 plus 5 divided by 100. If any number divided by 10 means you can add a decimal point after one digit, and if any number divided by 100 means you can add decimal point after 2 digits. So after solving this we will get this answer and then add it up, it will be 0.45. So you can see exactly we got the same number. So after all the calculation we can see here we got the same number 123.45. So our calculation was correct. In this way we have to solve for other number systems also by considering the base of that number system. Decimal number system has base 10, that's why we have taken the power of 10, and in other number system we have to consider their power. The next number system is binary number system, which is very useful in digital system to design electric circuit, as it works only on two voltage, on or off. If it is on means 1, off means 0. So it has only two numbers, 0 and 1. That's why it has base 2. It is also a positional number system. So let's consider one example. I am taking one binary number 100. It is a equivalent of decimal number 4. So let's try to find out the positional value of this number. So we have to take the power of 2, as the base of this number system is 2. So it will be 2 raised to power 0, 2 raised to power 1 and 2 raised to power 2. Now we have to multiply this positional value to the respective digits. So let's do it and try to solve it. What answer we will get? So it will be 1 into 2 raised to power 2 plus 0 into 2 raised to power 1, and again we have to sum it to 0 into 2 raised to power 0. So you know, no need to solve anything which is multiplied by 0. Ultimately we will get answer 0. So let's try to find out 2 raised to power 2 means 4. You can see here we got this 4 which is in the decimal number system. So we can write the base of decimal number system by 10, so that we will come to know that this 4 we are representing into a decimal number system. When we are dealing with different number system at the same time, we have to mention the base of it, so that it will be easy to understand that number we are representing in which number system. Let me explain for the fractional part also. Considering the same number, adding some random value, let's take 0, 1. So let's solve for the fractional part. You know, for the fractional part we consider the negative power. So it will be 2 raised to power minus 1 and it will be 2 raised to power minus 2. So let's solve it. 0 into 2 raised to power minus 1 plus 1 into 2 raised to power minus 2. We are multiplying this positional value to the respective digits and adding up. So again, no need to solve anything which is multiplied with 0. So we get here 1 divided by 4, and 1 divided by 4 will be 0.25. We took one binary number 100.01 which was in binary number system and converted to the number which is in the decimal number system. We have to specify the base like this, so that we will not get confused when we are dealing with more than one number system. Let's move forward with the third type of number system, that is octal number system. It has total 8 numbers from 0 to 7. That's why it has base 8. It is also a positional number system, same like binary and decimal number system. So let me take one example, 371.24. Now I am going to solve the fractional part together with non-fractional part, as you know how to solve it. The base of the octal number system is 8. So we are going to take the power of 8. The left side of the octal point will be the positive power of 8 and the right side of the octal point will be the negative power of 8. So it will be 8 raised to power 0, it will be 8 raised to power 1, 8 raised to power 2, and it will be 8 raised to power minus 1, 8 raised to power minus 2. Now let's multiply and find out. It will be 3 into 8 raised to power 2 plus 7 into 8 raised to power 1 plus 1 into 8 raised to power 0. Then we have to take the negative power. So it will be 2 into 8 raised to power minus 1 plus 4 into 8 raised to power minus 2. Solve along with me. So it will be 3 into 64 plus 7 into 8, and you know any number power 0 it will be 1. So 1 into 1 will be 1. And here we can write 2 into 1 divided by 8 plus 4 into 1 divided by 64. So 3 into 64 will be 192 and 7 8s are 56 plus 1. Here you can solve the way you want. Either you calculate 1 divided by 8, or here we can cancel also. 2 4s are 8 and we'll get here 16. So ultimately it is 1 by 4 plus 1 by 16. So let's solve for the 192 plus 56 plus 1 will become 249. 1 by 4 will become 0.25 and 1 by 16 will become 0.0625. So add the fractional part first. So it will become 249 plus 0.3125. So we got the final answer now, 249.3125. So this number is in decimal number system. That's why the base of this number is 10. So we started with octal number, that is 371.24 is an octal number, and we converted this number into decimal number system. So the base of this number is 10. Now it's time to study the last and the fourth number system, that is hexadecimal number system. This is also very useful number system because we can represent larger binary numbers into hexadecimal numbers. You might have seen the color codes will be generally into hexadecimal numbers. So it is consist of total 16 numbers. The digits are 0 to 9, same as decimal number system, but after that you cannot take digits, you have to take the alphabet A through F. So the base is 16. Same like other number system, hexadecimal number system is also a positional number system. So let's solve this example I have already written here. To solve this, draw the table and write the weight of that so that it will be easy to calculate. Multiply this weight with the digits. 3 into 16 raised to power 2 plus C into 16 raised to power 1 plus F into 16 raised to power 0. Then write for the fractional part plus 1 into 16 raised to power minus 1 plus A into 16 raised to power minus 2. Solve it further. 3 into the square of 16 is 256. Now let's substitute the values of C here, F and A. So as you know, so the value of C is 12. So 12 into 16 plus substitute the value of F also, it is 15. 15 into 16 raised to power 0 means 1, and then it will be 1 divided by 16 plus again substitute the value of A, that is 10. 10 divided by 16 raised to power 2. Okay, in the next step we will get 3 into 256 will be 768 plus 12 into 16 will be 192 plus we have 15. Now let's solve for this division. 1 divided by 16 will be 0.625 plus 1 divided by 16 square. 16 square is 256. So 1 divided by 256 will be 0.0390. So in the next step we will get 768 plus 92 plus 15 will be 975, and let's add this fractional part now, that is 0.1015. So finally we got 975 plus 1015, and this is in the decimal number system, that's why base 10. With the hope that you have understood all the number system, I am moving forward. The next topic we have to study the number conversion. In digital system, all these number system can be used. So we should have knowledge of converting the number from one number system to the other number system. In your syllabus, there are total 10 conversions. To make it simple, I have divided that 10 conversion into 3 sets. Look at this set. What it says, we have to convert binary number to decimal, octal number to decimal, and hexadecimal to decimal. These all conversions we have studied just now when we were discussing about the different number systems, right? What we were doing in that conversions, we were finding out the positional value or the weight and multiplying to the respective digits and adding up it. So if we are converting from binary, we have to take the base 2. If we are converting from octal, we have to take base 8. And similarly for hexadecimal, the base is 16. So this one set we have already studied. In this set, we have to convert to decimal from other number system. So keep in mind this set already we have studied. So let's subtract these 3 conversions from 10. So totally we have to concentrate on only 7 conversions. Don't worry, this again we will practice, but already you know the concept. Now look at this set. Here we have to convert from decimal to the other number system. So from decimal to binary, from decimal to octal, and from decimal to hexadecimal number system. So keep in mind the set name is from. So here what we have to do, as we are converting to binary, we have to do the repeated division by 2. If we are going to convert to octal, we have to do repeated division by 8, and if you have to convert to hexadecimal, we have to do repeated division by 16. So this set is also very easy to keep in mind. These 6 conversions are related to only decimal. The first set, from decimal to other number system, here we have to divide. In the second set, we have to convert to decimal, so calculating positional value and multiplying to the digit and adding them up. And the remaining are only 4 conversions. These are direct conversions. In that we have one set is this, where we are converting octal to binary and binary to octal. Similarly, in these 2 conversions we have to convert binary to hexadecimal and hexadecimal to binary. That I will teach you how to do. That is also very simple. So don't get confused in numbers conversions. It's actually very easy if you keep in mind these 3 sets which I have done for you. I will be teaching in the same sequence which are there in the textbook. So fix this image in your mind whenever there is a conversion problem. So let's enter into the world of number conversion. The first conversion we have to study is decimal to binary. Now keep in mind that 3 sets we have to convert decimal to binary, means from decimal we have to convert to other number system. So what was that? From means division. So according to that we have to do the repeated division, and as we are converting to binary, the base of binary number system is 2, so we have to do the repeated division by 2. So the number is 11, and now we have to do the repeated division by 2. So let's start it. So divide it. 2 5s are 10. Note down the remainder. We will get 1. Again divide it. 2 2s are 4. So we got the remainder again, that is 1. Then divide again till you will not get 0. You have to keep on dividing. So 2 1s are 2. We got remainder 0. So divide once again by 2. So we are dividing 0 times, but still we get the remainder 1. Now we have to record this remainder in the upward direction. So from bottom to top we have to note down this remainder. So what we got? 1 0 1 1. So here we have converted the decimal number 11 into binary number, that is 1011. If now you want to cross check whether you have done it correctly or not, how you can do? You know the procedure how to convert binary number to decimal number. Just write the positional value here or weight here, 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. Let's not calculate for 0, ultimately it will become 0. Now 2 to the power 0 is 1, 1 into 1 will be 1. 2 to the power 1 means 2, 2 into 1 will be 2, and 2 to the power 3 is 8, 8 into 1 will become 8. So 8 plus 2 is 10 plus 1 is 11. See, we got the correct answer. We have cross checked also. It's very easy. If you have not understood still, there is one more example I am going to take, that is easy one again. So let's try to solve it. So we have to divide the 5 again, repeated division by 2, and we have to note down the remainder. So let's divide it. 2 2s are 4. So 2 times we have divided, we got the remainder 1. Try it once again. 2 1s are 2, remainder is 0. Try it again because we did not get the 0 here. Divide once again by 2. So 2 zeros are 0. So we got remainder 1. Now note down this remainder from bottom to top. So it will become 101. So what was our decimal number? It was 5. That's why I am writing base 10, and we got the number 101, that is in the binary number system. Let's cross check it whether we have done it correctly or not. Write the positional value: 2 to the power 0, 2 to the power 1, 2 to the power 2. 2 to the power 0 means 1, plus 2 to the power 2 means 4. So you can see here 4 plus 1 is equals to 5. So we got the correct answer. In this way, take randomly any decimal number and try to convert it into binary. So you will get more and more practice and you will not get confused later. Let me give one random example to solve. Try to solve and write the answer in the comments below. Okay, let's take 121. It is in the decimal number system and we have to convert it into binary. As we are converting the numbers from decimal number system, there may be a chances that you may get fractional number also. So let's see how to convert the fractional part of decimal number system to binary. I have already written one number here. You know how to convert this non-fractional part 11. You have to just do the repeated division by 2 and note down the remainder. This I am leaving for you. Now I will explain you how to convert the fractional part to the binary. Let's take the fractional part, that is 08125. Here we are repeatedly dividing by 2. Now here we have to repeatedly multiply by 2. It is just the opposite of that. Calculate along with me. We have to multiply 2 to this number. So we get 1.625. Out of this number we have to remove the non-fractional part of this number. So I am going to remove the 1 from it. The remaining number, again I have to take that 0.625. Again we have to multiply by 2. So we will get this number 1.250. Now again take the 1 and the remaining part again we have to multiply. So we will get 0.5. Now remove the non-fractional part again. So we are getting 0. So the remaining is 0.5. Again multiply it by 2. Then we get here 1.0. Again remove the non-fractional part of this number and write down separately, that is 1. Now we got 0. If we multiply also 2 to that number, we will get again 0. So we will stop our multiplication here. Now we got these numbers. These we have to record in the reverse order. For non-fractional part, we were recording the number from bottom to top. Here we have to record the numbers from top to bottom. So what we got finally? It is 1, 1, 0, 1. So we got the conversion of 0.825 to this binary value. If you want to cross check, you know how to write the positional value for the fractional part. Start with the negative power of this, 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3 and 2 to the power minus 4. Let's not calculate for 0. So 1 divided by 2 plus 1 divided by 4 plus 1 divided by 16. So surely you will get the same answer. We are also getting 0.8125. If you are doing all these calculations correctly, you will get the same answer. Okay, let's solve one more example. So I will keep this non-fractional part to convert for you. I will be considering only fractional part. So we have to multiply by 2. So 0.75 into 2 will be 1.5. We have to take out 1. So the remaining is 0.5. Again multiply it by 2. We will get 1.0. Take out the non-fractional part of this. So we got the 0. Now you cannot multiply 0 with any number. So finally we got these numbers. So how you will record it? From top to bottom. So we got 1, 1 for the fractional part. If you want to cross check it, you can do it. So for fractional part, we take the negative power of 2, 2 to the power minus 1 and 2 to the power minus 2. So it will be 1 divided by 2 plus 1 divided by 4. Ultimately, if you calculate it, you will get 0.75. And you can see here this number and this number is same. In this way we have to calculate for the fractional part. One thing I have to One thing you can note down here, when we were converting fractional part to the binary, you may not get 0. In that case, you just do these steps for 4 times and then note down the number. So when we are converting the non-fractional part, we have to divide by 2. When we are converting the fractional part, we have to multiply by 2. It is just opposite of each other. Let's take one decimal number and practice this and write the answer in the comments below. Let's take one example, 521.17. So solve it. This we have to convert from decimal to binary. Let's move on to the next conversion, that is binary to decimal. Let's think that which conversion is this. I have shown 3 sets. In that it is belong to the second set, and even we studied this conversion when we were studying the 4 types of number system. So let's consider one example. Take randomly any number, that is 101. Okay, this binary number we have to convert to a decimal number system. So what we have to do here, did you recall? We have to take the positional value, multiply to the respective digit and add it up. So let's solve once again, and you are familiar with this procedure. So this is 1, this is 0 and this is 1. So what will be the positional value? It is 2 raised to power 0, 2 raised to power 1 and 2 raised to power 2. So let's solve it. So it will be 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 plus 1 into 2 raised to power 0. So you know 2 raised to power 0 will become 1. So let's not solve for multiplication with 0. It will be 4 and it will be 1. So you got 5. So ultimately we got this decimal number. Did you want to cross check it? You have just studied how to convert decimal number to the binary. Just do the repeated division and cross check it. So you can note that this is getting matched with this number. In this way you can do this conversion. These are very simple. Try practicing more examples. We studied 2 types of conversion. Now this is the third type, that is decimal to octal. We have to convert from decimal to octal. We already studied how to convert from decimal to binary by repeatedly dividing by 2. Now we have to convert from decimal number system to octal number system. So we have to keep dividing by 8. So let's solve it. So the number is 123 and we have to keep on dividing by 8. So we will get here 15. So 8 15s are 120 and the remainder is 3. Now let's divide again by 8. Here 8 ones are 8 and the remainder is 7. Again divide by 8. So here it is 0 times and the remainder is 1. So we will get answer 173. So our decimal number was 123, that is base 10, and we got this octal equivalent of the decimal number. If you want to cross check it whether you have done it correctly or not, you know how to convert from octal to decimal number system. We studied when we were discussing about different number system. So just take the power of 8, 8 to the power 0, 8 to the power 1 and 8 to the power 2, and then multiply these weights to the respective digits and add it up. You will surely get this answer. So you can cross check yourself whether you have done it correctly or not. Here you can see there is one more example. We have to convert 266 to the octal number. So let's try it. So the number is 266 and we have to record the remainder. So try dividing it by 8. It will go 33 times and the remainder is 2. Again we can divide by 8. So 8 4s are 32. So we will get remainder 1. Try to divide once again. So here we cannot divide. So 0 times we have to divide. So we'll get remainder 4. Again record the remainder from bottom to top. So we got the number 412. So our number was 266. It was decimal number system and the octal equivalent is 412. If you want to cross check it whether it is correct or not, you know how to do it. Take the power of 8, 8 to the power 0, 8 to the power 1 and 8 to the power 2, and multiply these positional values to the digits and then add it up. You will surely get this answer. Let's move to the next type of conversion, that is octal to decimal. We have studied this conversion when we were discussing about the different number system. Already we have studied how to convert binary number to decimal number. Now it is octal number to a decimal number. When we want to convert to decimal, what we do, we take the positional value and then multiply that positional value to the digit and add it up. So let's consider this example. Okay, let's solve it. The number is 24. So write the positional value of the number. So 8 raised to power minus 1, 8 raised to power 0, 8 raised to power 1, and then multiply this positional value to the digits. So we'll get 2 into 8 raised to power 1 plus 4 into 8 raised to power 0 plus 6 into 8 raised to power minus 1. So you will get 8 to the 16 plus 4 into 1 4, and then 6 divided by 8. So after calculation, this is 16 plus 4, we can write directly 20, and 6 divided by 8 is 0.125. So our answer is 20.125. If this is a decimal number and we started with our 24.6 octal number, you know how to change the decimal number to the octal number. We have to keep dividing by 2. So you can divide the 20 by 2, you will get this answer. If you want to cross check, you can cross check it. 20 divided by 8. Okay, there is one more number. Let's practice it. So let's write the positional value of this number. So let's multiply it. 3 into 8 raised to power 2 plus 7 into 8 raised to power 1 and plus 2 into 8 raised to power 0. So 3 into 64 plus, this is 56, and plus 2. Now 3 into 64 will become 192. So 192 plus 56 plus 2. So we got the final answer. So this is the decimal equivalent of 372. If you want to cross check, you know how to cross check. Just keep dividing this number by 8. Okay, now let's understand octal to binary. Not from decimal, not to decimal. So this conversion is from that third set what I have categorized to make it simple. Now how to convert octal to binary? If you remember, I have written there direct conversion. So direct conversion means what? Consider this number, this is an octal number, and we have to find out the binary equivalent of that. So we have to directly convert these octal numbers into the binary number. So we have to find out the binary equivalent of 2, binary equivalent of 7, and binary equivalent of 4. Now how to find out this? Let me give you a simple way to find out. You know, every bit has its own positional value or weight. In binary number system, the positional values we take, that is 2 to the power 0, 2 to the power 1, 2 to the power 2. It means it is 1, it is 2, and it is 4. 3 bits are sufficient when we are converting from octal to binary, because 0 to 7 octal digits we can represent using only 3 bits of binary number. So let's try to find out the equivalent of all the octal numbers. So the first octal number is 0. So we will write all the bits at 0. The next octal number is 1. We will place 1 at the positional value 1, and the rest of the bits are 0. Now the second one is 2. Now you try to find out where is that position. So this is 2. So place 1 at the column of 2 and the rest of the bits write as 0. The next number is 3. How you will get 3? When you will add 2 and 1, you will get 3. So at the column of 2 write down 1, and in the column of 1 also write down 1. Other bit will be 0. Now let's try out for 4. So at the column of 4 write down 1, other bits will be 0. Similarly for 5, so try out all the combinations and write the 1 at that column and other bits will be 0. So how you will get it 5? When you will add 4 and 1. So at the column of 4 write down 1, then at the column of 1 we will write down 1 and in the other column 0. Now how to find out for 6? What you will add so that you will get 6? 4 and 2. So write down the 1 here in the column of 2 also and the other bit will be 0. Now the last number of the octal number system is 7. So how you will get 7? When you will add 4, 2 and 1. So all the bits will be 1. In this way we can find out the binary equivalent of any number. So now what is the binary equivalent of 2? 2 is 0, 1, 0. So write down here 0, 1, 0. Now next number is 7. So the binary equivalent of 7 is 1, 1, 1. And then binary equivalent of 4 is 1, 0, 0. So our final number is 1, 0, 0, 1, 1, 1, 0, 1, 0. The octal number was 472 and we got the binary equivalent of that number. So let's try one more example. 1, 3 and we can take it 6. So try to convert it. This is an octal number. We have to find out the binary equivalent of this. Now this is 1. Then this is 3 and this is 6. So find out the binary equivalent of these numbers. So what is the binary equivalent of 1? That is 0, 0, 1. What is the binary equivalent of 3? 0, 1, 1. What is the binary equivalent of 6? 1, 1, 0. So our final number is this. In this way, take randomly any number and try to find out the binary equivalent of it. No need to write this full table also. Just find out which combination you need and place 1 for that and the rest of the bits will be 0. Now the sixth conversion is just the reverse of it. If you have understood how to find the binary equivalent of the octal number, you can do the reverse of it. So from binary to octal, what we have to do? We have to do the grouping of 3 bits. As I told, for octal number system, only 3 bits are sufficient to represent it. So make the grouping of 3 bits starting from right. So these 3 bits one group, then 3 bits and the remaining 3 bits will be one group. So I have written here 0, 1, 0, 1, 1, 1 and 1, 0, 0. As I told, there is no need of keeping in mind whole table. Just find out from this number at what position there is a 1 bit. You know this is 2 raised to power 0, 2 raised to power 1 and 2 raised to power 2. So at what place the bit is 1, that is 2 raised to power 1 means what? This is a octal equivalent of 2. Now what about this number? So this is also again, if you can do directly it's fine, otherwise you can write here and you can find out. So 4 plus 2 plus 1 means what? It is a 7. Now again try to find out directly for this. This is the first bit, this is second bit and this is the third bit. Means what? This is 1, this is 2, this is 4. So at the place of 4 we have 1 bit, means it is a octal number 4. So our binary number is converted into octal number. In this way you take randomly any number and try to convert it. If you want to cross check, you can do the reverse process and cross check your answer. Just try to find out this number now, 1, 0, 1, 0. We have to find out the octal equivalent of this number. Now what is the first step? First we have to group this number into bits of 3 starting from right side. So if you don't have sufficient bits, you have to add 0 on the left hand side. So starting with right side, I have got one set, that is 0, 1, 0 and there is one more bit remains, that is 1, but it is not of 3 bits. So what we can do? We can just add 0 in front of it. Now it is a group of 3 bits. Now let's try to find out the octal equivalent of this binary number. So this is again 1, this is 2, this is 4. So 1 is at the place of 2. So this is the equivalent 2. This is 1, this is 2, this is 4. So we have 1 bit at the place of 1. So we got the octal equivalent of this binary number. Let's continue the conversion from decimal to hexadecimal number system. We have studied till now decimal to binary number system, then we studied decimal to octal number system. Now we have to study decimal to hexadecimal number system, and if you remember, this set is from decimal to other number system. When we have to convert, we divide repeatedly by the base of that number system. So here we divided by 2, here we divided repetitively by 8, and here we have to divide repeatedly by 16. So let's solve this example. So the number is 423 and we have to do the division by 16. If we will divide it, I think 26 times I can divide it, the remainder will be 7, and now again we have to divide by 16. So 16 ones are 16, remainder is 10, but we cannot write 10 here because hexadecimal system contains numbers from 0 to 9. After that, if you want to write 10, so we cannot write 10. Instead of that, we have to write A. So this will become A, and again we have to divide by 16. So now we will get it 0, remainder will be 1. Now we have to note down these remainders from bottom to top. So our answer is 1A7. So we started with 423, that was a decimal number, and we converted into a hexadecimal number system. If you want to cross check, you know we have studied this when we were discussing about the different number system. Just take the power of 16 and these positional values, and you can multiply this positional value to the digits and sum it up. You will ultimately get this number if it is correct. Hope you are getting my point. There is one more example. Let me do it for you. You can try another examples also, and you can cross verify yourself. So let's solve together. You also solve along with me. So our number is 214. We have to record the remainder here. So I will write it. So divide by 16. It will go, I think, 13 times, and the remainder is 6. Again divide by 16. Now we cannot give, so 0 times we have to divide, remainders will be 13, but we cannot write 13, you know. So the B will be 11, and C will be 12, and D will be 13. So we are getting 13 means we have to write it here D, because D is equals to 13. Got the remainder from bottom to top, so we got the answer D6. Try solving more examples. Okay, let's discuss this 8th conversion. This is very easy and you know how to do it. It is a conversion from hexadecimal number system to decimal number system. It is that category of conversions where we have to convert to decimal number system. So we have studied till now from binary to decimal, then we studied octal to decimal. Now this is hexadecimal to decimal. You know, in this type of conversion, what we do, we take the positional value, multiply the digit and sum it up. So we have one example here. Let me write directly. So I will write it here. 2AF, this is 16 raised to power 0, 16 raised to power 1 and 16 raised to power 2. It will be 2 into 16 raised to power 2 plus A into 16 raised to power 1 plus F into 16 raised to power 0. So let's continue it. The square of 16 is 256. The value of A is 10, so 10 into 16. The value of F is 15, and 16 raised to power 0 will become 1. So I will write it 1 here. So 2 into 256 is 512 plus 10 into 60 will be 160 plus 15. So we got the number 677. It is in the decimal number system. Okay, let's practice one more example. Solve along with me. So I will write the positional value here itself. this is 16 raised to power 0, 16 raised to power 1. Here 16 raised to power minus 1 and 16 raised to power minus 2. So let me write 5 into 16 raised to power 1 plus 6 into 16 raised to power 0 plus 0 into 16 raised to power minus 1 plus 8 into 16 raised to power minus 2. Okay, solve it now. It is 5 into 16 plus 6 into 1 plus, it will become 0 because multiplication with 0 will be 0, and this will be 8 divided by 16. So now let's solve it further. 16 5s are 80 plus 6 plus, oh, this is a 16 square, so 8 divided by 256, right? Then this is 86 plus, we are getting this fractional part as 0.0390. So after adding we'll get 86.0390. So this is our final number which is in the decimal. Till now we studied 8 conversions and there are 2 more, and that too very easy. Now we have to study binary to hexadecimal and hexadecimal to binary, and this is a direct conversion. We have already studied how to convert binary to octal and octal to binary. Here also same procedure we have to follow, but in case of binary to octal we were considering 3 bits. But in case of hexadecimal, we need to go for 4 bits because we cannot represent 16 digits of hexadecimal numbers. So consider an example. We have taken one binary number and we have to convert it to a hexadecimal. So in this conversion, we have to make a group of 4 bits. So this is one group, this is another group, and the remaining there is one more group. If we don't have sufficient bits, we can add that many zeros. Now how to find out the hexadecimal equivalent of this binary? I have already explained while we were converting from binary to octal. So let me explain once again. You know the positional value of the binary number system is the power of 2. Now we have to take one more bit, that is 4th bit, because 4 bits are required to change to hexadecimal number system. So it will be 1, this is 2, 4 and 8. So let's try to understand how to find out this. So let's start with 0. 0 means all the bits will be 0. Now we will consider 1. So if I want 1, I should write 1 in the 1's position. So the rest of the bits will be 0. Now if I have to find out the binary equivalent of 2 and I could see 2 here, so write 1 bit here, the rest of the bits will be 0. Now check out for 3. If I want 3 means I have to add 2 and 1. So at the place of 2 and at the place of 1 I have to write 1 bit, rest of the bits are 0. Similarly for 1, try to do the combinations for this. 4, we can see 4 is here, so we can write 1 bit here and the rest of the bits are 0. Now similarly for 5, how you will get 5? 4 plus 1, so write 1 at the place of 4 and at the place of 1, rest of the bits will be 0. Now try to do it for 6. How will I get 6? 4 plus 2. With this combination we can write 1 here and 1 here, rest of the bits will be 0. Now try to find out for 7. How will I get 7? 4 plus 2 plus 1 will be 7. So I should write 1 here, 1 here also and 1 in this column also. The rest of the bits will be 0. Okay, let's do it. Now we have to find out the binary equivalent of 8. So I will write 1 here and the remaining bits will be 0. For 9 I can do 8 plus 1. So 1 bit is here, 1 bit is here, remaining bits will be 0. Now try out for 10. How will I get 10? 8 plus 2. So 1 bit here, 1 bit here, remaining bits will be 0. How will I get 11? 8 plus 2, 10 plus 1. So 1 bit is here, then 1 bit is here, 1 bit is here and the remaining bits will be 0. So here we have to write 1, 0. Now let's find out for 12. 12 will be 8 plus 4. So 1 here, 1 here, remaining bits will be 0. 13 will be this 8, 4 and 1, remaining will be 0. Now let's try out for 14. 14 will be 8 plus 4, 12, and 13, 14. This bit will be 0. Now for 15, I have to write all the bits as 1. So no need to keep in mind this table, just try to find out with the combination of the numbers and write 1 for that, the remaining bits will be 0. Now 1010 we have to convert to the hexadecimal. You can check now here. Instead of keeping in mind this whole table, there is one more simple method. Just write the positional weight here, 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. And no need to solve for 0, so just ignore this and solve for only 1. So 2 to the power 3 will be 8 and 2 to the power 1 will be 2. So this is 8 plus 2, 10. So the binary equivalent of this number is 10. You can see here this is 1010, but we cannot write 10 in hexadecimal number system. Instead of that we should write A. Similarly solve for it. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. No need to solve for 0. 2 to the power 3 will be 8 plus 2 plus 1. So it will be 11. Check out this whether you are getting the correct answer or not. 1011. And for 11 we have to write B. We cannot write 11 as there is no number like 11 in hexadecimal number system. Now let's find out for this. No need to solve for 0. So this is 2 to the power 1. 2 to the power 1 means 2. So ultimately we can write 2. So our final answer is 2B A. Okay, the last conversion is the reverse. Okay, now the last conversion. Okay, now the last conversion is just the reverse of the previous one. There we were converting binary to hexadecimal. Here we have to convert from hexadecimal to binary. So that is also a direct conversion. Let's take one example here. This is a hexadecimal number and we have to convert it to binary. Now without keeping in mind this whole table, you have to convert it because you cannot keep in mind the whole table. That I know. So now how to find out the binary equivalent of 2? Just now I have explained. If you don't know, just write down the positional value of the binary number system and then try to find out the combination, with which combination you will get that number, and write the one bit for that and other bits will be 0. So how you will get it? 2 means here you have to write 1, other bits will be 0. So the binary equivalent of 2 is 0 0 1 0. Keep in mind in hexadecimal number system we have to consider 4 bits. And let's try out for F. The value of F means it is 15. How you will get it 15? It is 8 plus 4 plus 2 plus 3. So all the bits are 1. So the binary equivalent of 1 is this. Now let's try out for 9. How you will get it? 9. It is 8 plus 1. So write the 1 for 8 and 1 bit for 1. So we will get it 9. Other bits will be 0. So the binary equivalent of 9 is 1001. In this way we got the binary equivalent of this number. Write down the final answer. In this way we studied the conversion of numbers from one number system to another number system. It is very easy and very interesting also. Try to solve more problems to get more and more practice. After studying different types of conversions, now it's turn to study the binary addition. For that we need to follow the 5 basic rules. The first rule is 0 plus 0 will be 0, 0 plus 1 will be 1, then 1 plus 0 will be 1, 1 plus 1 will be 1 0. So we should write 0 and then we have to carry 1. If there is a 1 plus 1 plus 1, we should write the answer as 1 and we should take the carry 1. Let's consider one simple example. There are two binary numbers and we have to perform the addition. Let's add 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 will be 1, 1 plus 1 will be 0 answer here we should write and we should take carry here. Then 1 plus 1 plus 1 will be 1 1. By keeping in mind these 5 rules, you can solve some more examples. Let's move on to the next topic, that is the encoding system. We saw how computer represent digits. Now it's turn to understand how the computer represent letters, symbols and special characters like punctuation marks, etc. For that we have different coding system. The first one is ASCII coding system, then the second one is ISCII, and the third one is Unicode. Let me explain in short what all these encoding systems are. The first encoding system is ASCII code. The full form is American Standard Code for Information Interchange. All the characters what you see on the keyboard has some alphanumerical code associated with that. You can see in the table in ASCII code we have the numbers from 0 to 127 to represent all the characters. So you can see here this is 0 and this is 127. Total 128 possible values we can store with this ASCII table. There is another encoding system. It is used for Indian script. In India we use a lot of languages, so for that we have this code, that is Indian scripts code for information interchange. There is one more encoding system that is called as Unicode, because we saw two encoding system, one is American and one is Indian. So to universally represent all the languages, this coding system is used. So there are three different types in that: UTF-8, UTF-16 and UTF-32. The first one is UTF-8. It uses 8 bits, that is called as an octet, to represent the number. So in first octet we can represent the value 0 to 127 and the remaining values has 2 octet, 3 octet and 4 octet. The next one is UTF-32. It uses exactly 4 bytes, and there is one more variation, that is UTF-16. It uses 2 or 4 bytes. So this chapter covers the different types of number system and the conversion of numbers from one number system to another number system. Hope you have understood this concept. If you have any doubt, please write in the comments below. In the next video, I will be explaining the chapter 3, Boolean logic. So till then, keep studying. See you in the next video.